welcome to this video on pressure and kinetic molecular theory. I have a question for you to start off with. What is it like to be corn on an airplane? Do you think their ears pop? But really, that's a good segue because it's all about pressure. You know, when you go up in an airplane, it's pressure changing. And we're going to first start by figuring out what pressure is and then relate it to what's going on with molecules in substances, especially gases. So after this lesson, you should be able to explain how force and area relate to pressure, and then use kinetic molecular theory to relate the motion of particles to pressure. So that's what we're trying to get across. Okay, so first off, what can we think about as a good way to think about pressure? Well, how about something that you, especially if you are a driver, should really pay attention to, the pressure of your tires. So most modern cars have a system where there is a small sensor inside of the valve that you use to inflate the tire that detects the pressure and sends it to the car's computer system using a small, it's called RFID device. So it's actually able to communicate, and if it is not at the recommended pressure, it actually usually gives you something that looks like this, a light. And hopefully, if you have a really nice car, it'll tell you which tire has a pressure issue. But if not, you may find yourself, as I have done many times, checking every single one manually and trying to make sure they all have the same pressure. And why does pressure matter when you have car tires? So properly inflated tire is going to have the correct amount of traction, the correct amount of the tire on the road. That's what the tire is designed for. It'll give it a nice wear pattern, so it'll wear evenly and won't have weird spots. If it's underinflated, you can see here it tends to bulge a little bit. That can cause it to not handle as well, so the car could slip a bit when turning. It also can damage the tires. And if it's overinflated, if there's too much pressure inside, you can actually end up with poor grip because less of the surface area of the tire ends up contacting the road surface. So, important thing, if you're learning to drive, remember to check your tire pressure, and while your car may tell you if you have a tire pressure problem, you still need to figure out which tire it is and how to make sure you get the right tire. An especially important issue in the winter time when the temperature affects the pressure quite a bit. Okay, so what is pressure? Pressure is a measure of force per unit area, and so here's something to take notes on. And if I go a little too fast here, you just pause the video, go backwards if you need to. But pressure is force per unit area. So we take a force, a push or a pull, and we just divide it by how much area that force is spread out over. So very simply, it's P equals F over A. Pressure is force divided by area. Here are some common units you're going to see for pressure. So if you are checking your tires, your car tires, or even bike tires, you're going to check them in pounds per square inch. Pounds per square inch, which is abbreviated PSI. And if you ever see one of these, this is a manual pressure sensor that you can get for your car, and you simply stick this thing on there, squeeze it onto the valve, and the valve will push back against this, and it will shoot out to a certain number, and that number is the PSI. So it looks like this car's tires are just over 30, which is where most cars need to be. So that is using our American system, pounds being the force per square inch, and square inch being the unit for area. In the metric system, the official unit for pressure is the Pascal. The Pascal, and a Pascal is 1 Newton of force per 1 square meter of area. 1 Newton of force per 1 square meter of area. And there's this alternative unit that we may come across multiple times, which is called an atmosphere. And an atmosphere is literally just the amount of the amount of pressure that the atmosphere has at sea level on Earth. And it's because there is an extraordinary amount of air above you. Air has mass, and so the amount of air above you actually does push down with a certain pressure. That pressure happens to be equal to about 14.7 pounds per square inch. So it's not insignificant. It's an interesting question why we don't feel it, but it's not insignificant. And that is 1 atmosphere. So sometimes we just look at pressure in terms of how many atmospheres might be pushing down on something. Okay, how do you calculate pressure? Here is an example problem that we can use. So let's say I weigh 175 pounds, and my feet are on an area of 25 square inches, right? How much pressure am I putting on the floor, or really the specific parts of the floor under my feet at this time? So let's work that out. I'm going to open a little whiteboard thing I can use here. So remember what we said. We said pressure is equal to force divided by area, right? And so we want to know this pressure. That should be a P. That's the worst P ever. That P is equal to the amount of force, which is 175 pounds, divided by the area in square inches. And I gave you that, 25. Let's make sure we put our units in here. So 175. LBS is our old pound symbol, and 25 inches with a superscript of 2 to indicate they're squared. And so that should give us 25 into 175 goes 7 times. So that becomes 7 PSI, 7 pounds per square inch. Okay, so that's a simple, straightforward American system calculation for that. Let's try another one instead using our metric system. So let's say that I can hit a nail with a hammer using 200 newtons of force. If the nail has an area of 0.04 square meters, how much pressure will be exerted on the nail? So we'll switch back and another whiteboard space here. So remember again, I always like to write out the formula that we need to use. So pressure is force divided by area. So the force is 200 newtons, and the area is given to us as 0.04 square meters. And then we just simply need to divide. Let's get ourselves a calculator. Remember, you can always just Google the word calculator, and you'll get a calculator. Look at that. So 200 divided by 0.04 is 5,000. There we go. So 5,000, there's 3 zeros, 5,000 newtons per square meter. Remember, we said that that is the same thing as a Pascal, right? So it's 5,000 pascals, or PA. PA is the symbol for Pascal. Okay, well, let's get back to how this relates to molecules and substances and gases, and that's all about the kinetic molecular theory. So what is this kinetic molecular theory? It's something that describes the properties of atoms and molecules in terms of kinetic energy and temperature. Just a quick note here. We talk about it as molecular theory because usually we are interested in molecules. It's really about atoms or molecules, right? It's about particles, individual particles. Sometimes they're atoms, most of the time they're some kind of molecule. And it's in terms of their kinetic energy, right? Their energy of motion and temperature. It's most commonly used to explain the behavior of gases at the molecular level, but it really does apply to any substance whatsoever. It's just that it explains more interesting things with gases. Okay, and something you should already know is that the average amount of kinetic energy of the particles in a substance increases with temperature. So this is a diagram you've hopefully seen before, which is states of matter, and you can see that in a solid you've got these neat orderly particles, molecules if you will. In liquid, they're a little less orderly, they're just slightly more spaced out, and they're moving a little bit faster, right, because the kinetic energy is increasing. And then in a gas, you've got lots more space, lots more motion. In fact, this diagram doesn't at all show the scale. The distance between the molecules in a gas is vastly greater than it is between liquids and solids. And then if you really keep increasing the kinetic energy, you can actually get to the point of separating out the electrons from the rest of the atoms and create what's called a plasma. And so changes in kinetic energy of particles occur even within the same phase, So we were already talking about how different phases of matter have different amounts of kinetic energy, but you can also vary the kinetic energy while still staying in the same phase. And here is a little demonstration of that, a little animated demonstration of that. So this is a little demonstration. And unfortunately, I have to move some of these molecules out of the way. But these are all water molecules, and they're bouncing around, right? So imagine this is just kind of a glass of water or something like that. And you can see it's at the coldest, and what happens when I make it hotter? Well, they start vibrating, and they start moving around and bouncing around more. I gave it more energy. Doesn't actually matter what phase they're in, they're going to start moving more. You can see they're vibrating and bouncing off each other and off the sides of the container, or really the side of the screen here. Okay, so those changes can take place even in the same phase, even without a phase change. That means that liquids can take up different amounts of volume. Solids can take up different amounts of volume depending on their temperature. But the biggest difference with that really comes in gases, where the particles are much farther apart. So we're going to go through gases in kinetic molecular theory, and we're going to, so it's gases that really provide the evidence that make up kinetic molecular theory. So we're going to go through the evidence and show you how that leads to this five-part theory. So the first evidence is that scientists noticed was that gases are compressible. In other words, you can reduce their volume pretty easily. If you take a solid of something, it's pretty hard to squeeze it down to a smaller size. Without kind of breaking it, and even doing that doesn't necessarily reduce the volume. But gases are very easy to compress, and we have lots of examples where we can do that, and it's one of the reasons why gases don't make good, say, fluids for hydraulics, because hydraulics need to not be compressed, and air compresses pretty easily. And of course, this is a principle behind how the internal combustion engine works. This is an example or a diagram of an internal combustion engine, and you can see the gases get compressed and then they get forced back down by the force of combustion, which pushes them back against the cylinders and moves the engine. And so what this tells us about or leads to in terms of the theory is that gas particles must be really tiny and the rest of it is empty space, right? So that most of, if you say, look at a balloon, most of what's in the balloon is empty space, and there are little tiny gas particles moving around, but most of it is empty space, and that's why we can squish it down to a smaller size. Here's the second part of, our second piece of evidence that leads to the second part of kinetic molecular theory, and that's that gases don't clump together in any way. And this isn't totally, completely true, but for the most part it is, especially when we're learning generally about gases. But if the particles really like to stick together, we wouldn't have a nice even balloon shape, right? Like this, right? We would probably have a weird lumpy balloon. But because they, generally speaking, don't attract each other, they spread out as much as possible, and we get even shapes when we try to put a container around a gas. Okay, third part is that gases mix together pretty quickly, right? So you can see that, for example, in something like a wildfire. You see the smoke coming up, and then it doesn't take very long for the smoke to spread out, and you can no longer see exactly where the smoke plume is, but you just see kind of a general haze in the sky. Because gases mix together fairly quickly. It doesn't take all that long for that to happen. And what that tells us, what that leads to in terms of the theory, is gas particles move in this constant, rapid, random, straight line motion. So the particles are moving all over the place. They're going very quickly. They're not necessarily going in any specific direction, but they're bouncing off each other, and they're bouncing off whatever happens to be nearby that's not a gas, like the container or what have you. So more evidence supporting more parts of the theory. And then gases can keep constant pressure. So imagine, for example, a bike tire. You inflate it, and then you go off for your bike ride. If the gas couldn't keep the pressure, then your bike ride wouldn't last very long, and your tire would be flat, and you wouldn't really go anywhere. But gases are able to keep up that constant pressure because they're constantly bouncing and they're constantly in motion. So inside of your bike tire here, there's a bunch of gas particles bouncing off each other and bouncing off the sides of the tire, and that's what's keeping that tire well inflated. And you might be saying, well, but yeah, I mean, eventually my tire goes flat and I have to pump it back up again. That's true. That's because there's not a completely perfect seal between the tire and the rim, which allows some of the air to eventually escape. So it's not about the gas, it's just about the container, and the container isn't perfect. But because we see this constant pressure, we see that gas particles are bouncing off of each other and off of the container they are in, and that's constantly happening. And then finally, gas volume increases as temperature increases and vice versa, right? So the average kinetic energy of gas particles can be measured by temperature. So what this is telling us is that temperature is a good, I'm sorry, that should not be volume, that should be pressure. Gas pressure. Aren't you glad I can edit these things on the fly? So the pressure increases as the temperature increases. So if you take a sealed container of gas and turn up the temperature, you're going to get more pressure. Or the opposite, and that's actually why I have this picture here, because one issue you may find when you have a car is that in the winter your tire pressure starts to be lower because the temperature is going down, which is causing the pressure in the tire to also go down. And so that's telling us that the average kinetic energy of gas particles can be measured by temperature. So temperature is actually that. It is a measure of the average kinetic energy of particles. And in this case, we're just relating it to gases. Okay, and so this is just a final chart giving you all of the parts of the kinetic molecular theory if you need to write them down and make sure you know them. But hopefully this is all coming together to give you a sense of both how we can see what's going on at a molecular level and relate it to the behavior of gases. See you next time.